We keep asking when will AGI happen, but does anybody know if AGI is even physically possible? In the previous episode, we went over the top 5 reasons why AGI will never happen. Now, that video got a lot of backlash, and to be honest, I wasn't expecting it to be such a contentious topic. But then I realised, maybe I was going about this the wrong way. Today, I wanted to double down, except this time I wanted to make my argument a little less conceptual and a little more grounded in physics instead. Before we dive in, perhaps we should start by defining what we actually mean by AGI, because general intelligence is a very specific thing. It's not pattern matching, or playing chess, or generating text. General intelligence refers to a system that can continually learn and adapt over time, the way a human can. This means being able to handle situations the agent hasn't seen before, make predictions from limited information, and transfer what it learns in one context to a completely different one. In other words, AGI isn't about being able to solve a given set of problems. It's about having an innate capacity for learning and adapting to any kind of problem that's sent its way. Just so we're clear here, LLMs do not qualify for general intelligence. LLMs stop learning the moment they're trained. The model's weights are frozen at deployment. If you wanted an LLM to learn something new, you'd have to manually update the model. ChatGPT can't initiate or perform these updates on its own, so it can't develop new abilities by itself, which is a fundamental requirement for general intelligence. I gave a more thorough and precise definition in my last video, so if you want the full breakdown, go check that out. But ultimately, I think that there's a better way of thinking about general intelligence, because this ability to continuously learn and adapt isn't just a feature, it's a symptom of something deeper. General intelligence, as we normally imagine it, requires an agent that can think for itself, a system with its own motivations, its own goals, and the capacity to pursue them across any domain. You can ask an LLM to generate the image of a cat, but the LLM won't do anything unless you prompt it to. In this sense, LLMs aren't agents, they're tools. An axe doesn't chop wood unless there's a human wanting to make a fire. A true AI agent would require the open-ended, adaptable, domain general intelligence that we typically associate with living beings. And in science fiction we see it all the time. From Ava in Ex Machina, to Sunny in I, Robot, and even WALL-E. These are beings that aren't just smart, they are self-directed. So this is the definition that we'll be using. A being that is self-directed and that can think for itself. But defining general intelligence wasn't really the issue here. The real challenge is to show why it will never be artificial. The human brain is home to around 100 billion neurons. Now, each of these neurons might form around 1,000 individual connections, or synapses, which means that on average, the human brain has around 100 trillion connections. In computational terms, you can think of a synapse like a logic gate, the fundamental unit for information processing. In silicon, the closest equivalent would be a transistor. Now, 100 trillion transistors might sound like a lot, but consider this. A modern GPU like the NVIDIA H100 used in AI data centers around the world has around 100 billion transistors. With only 1,000 of these, we could easily match that figure. And 1,000 GPUs really isn't that much. I mean, sure, it's got a price tag of around $25 million, and it'll fill 20 server racks. But compared to some AI data centers today, that's nothing. Theoretically speaking, using our current technology, we could match the computational capacity of a single human brain with hardware that would fit inside a single shipping container. So then, why aren't we? Let's imagine an AI future. The year is 2027, and humanity has mapped the entire neural configuration of a single human being. Her name was AGIRA, and now we have every neuron, every synapse, every connection in her body. The goal is clear. Recreate this singular network of logic gates, not in flesh, but in silicon. We've named her digital twin AGIRA, a tribute both to the woman she mirrors, as well as the AGI she aspires to be. The 100 trillion transistors in her neural network fit in an area no bigger than a single square meter. But this network of transistors alone isn't enough. In order for AGIRA to actually experience anything, her sensory neurons would have to be stimulated. They'd need to be connected to something that's actually capable of generating sensation. So, imagine we built her an artificial body, one outfitted with 10 billion individual sensors, pressure sensors, heat sensors, vibration sensors, all wired directly into her sensory neurons. Now, if we wanted AGIRA to feel a jolt of pain in her leg, all we'd have to do is hit her leg. The impact would trigger the corresponding sensors, fire the connected neurons, and in principle, AGIRA should feel the pain exactly as a human would. But experience isn't confined to a single point in time. When somebody tickles you, the sensation isn't trapped in a single moment. You don't feel one static jolt of pressure on your skin. You feel a motion, a foreign object brushing lightly across your body, a sensation that unfolds over time. The sensation is continuous, relational, and inherently dynamic. So here's the problem. Even if we had captured every relevant detail of AGIRA's neural system, ion channel states, neurotransmitter concentrations, the works, this would only ever be a snapshot of AGIRA's nervous system. You see, the human brain at one instant in time is not the same brain even a second later, because unlike a computer, the brain is not a static circuit. It's plastic. It's constantly rewiring itself, strengthening some connections, weakening others, creating new pathways, pruning old ones. And this isn't optional. This kind of ongoing reconfiguration is what general intelligence is. In order to have general intelligence, a being must have the ability to reconfigure its cognitive architecture on the fly, just as biology does. A dog that hears a bell before being fed will literally rewire its own brain. The neurons linking sound to reward fire together, strengthen together, and reshape the very circuit that learns the association. Brains don't just process information. They change the very architecture that processes the information. You don't just update the data, you update the machine that's doing the updating. Because general intelligence doesn't live in the layout of the brain. It lives in the ability of that layout to continuously change itself. Okay, so let's imagine we figured out a way for AGIRA to reconfigure on the fly. Let's say we have a dedicated supercomputer monitoring every artificial synapse, tracking the current flowing through each one. This metacomputer decides which connections need to be strengthened, which ones need to be weakened, and then uses hyper-specialized lasers to literally reprint the circuit in real time. Brilliant, right? Well, keep in mind that the technology we currently use to print patterns onto silicon, EUV lithography, requires hyper-specialized machines the size of shipping containers, costing hundreds of millions of dollars each, and that's for printing a static chip. Now imagine doing that 100 trillion times a second. Let's assume that all of this is possible. Let's assume that we've replicated an entire neural network, wired up 10 billion sensory receptors, built a supercomputer capable of monitoring and rewiring every synapse in real time, all while the system is continuously trying to learn, reason, and adapt. Well, that's a lot of moving parts. If you've ever owned a car, you know how quickly things fall apart. A loose bolt, a worn bearing, a tiny leak, one failure cascades into another. Now scale that fragility up to a machine with 100 trillion moving parts. For AGIRA to experience the world instead of static and noise, every component would need constant monitoring, repair, and replacement. Because unlike a human brain, none of this system maintains itself. And that's the part that we always forget: entropy. Entropy, or the second law of thermodynamics, states that for every energy transfer, the total entropy of the universe, its disorder or randomness, increases. In a way, this is sort of like Murphy's law, right? The universe always tends towards its most chaotic states. What this means for AGIRA, of course, is that every component in her vast neural network, every inch of her supercomputer, is going to break down eventually. The GPUs that we currently use in AI data centers, for example, have a lifespan of around 3 years. That's just the median lifespan, mind you. Some may break down well before, others may last a lot longer. But really what's important here isn't how long a given technology lasts, it's the fact that it needs to be continually replaced. And you might be thinking, oh well, that's just current technology. Planned obsolescence is built into these products because that's how companies make profit. If only we used more durable materials, then we'd be fine. But no, that's just not how this works. Entropy is unavoidable. All things tend toward disorder. That's just the way of the world. Even if we did find a way to improve the durability of these materials, we're only just pushing back the date at which they'll need to be replaced. And that figure of 3 years was based solely on wear and tear brought about through computation alone. But we're now talking about firing lasers at live wires 100 trillion times per second. Imagine how often you'd need to take that kind of a machine to the mechanic. Every rewiring introduces the possibility of error. Every calculation, every laser pulse, every shift in a connection increases the odds that something will fail. No machine, not even one built to mimic a human brain, can escape this reality. Perfection is impossible. Eventually, all things break down. We might imagine starting with a perfectly functioning machine. AGIRA experiences a tickle as we caress the sensors in her artificial hand. Everything works as intended. But as those parts inevitably decay, what was once a coherent sensation in the AI's mind gradually unravels. The crisp signal of touch slips into randomness. The precise pattern of firing dissolves into static, and the experience fades into meaningless noise. Now we can argue over how long it might take before the sensation dissolves into static, but the fact is, no matter how perfect the design, entropy ensures that order will not last. But let's say we have a plan. Let's say we build a system that not only fires lasers at wires, it also monitors every single component of AGIRA's network, every sensor, every synapse, every strand of wiring. The moment a part shows the slightest sign of wear, it gets replaced, recalibrated, or repaired. In theory, this could keep her running indefinitely. But think about what that would actually entail. We're talking about 100 trillion artificial synapses, 10 billion sensors, miles of wiring, and countless microcomponents, all being monitored, corrected, and renewed in real time. Every replacement requires a level of precision far beyond any technology we've ever imagined. Every delay, every misstep, risks a cascade of failures that would unravel the system. And that's just for AGIRA's hardware. You'd also need to monitor the supercomputer itself, the lasers, the cooling system, the power supply, everything that makes the rewiring possible in the first place. Every part must be perfect, all the time, or the illusion of coherent experience collapses. The more you think about it, the more the scale becomes staggering. We're no longer talking about maintaining the machine. We're talking about maintaining the machine that maintains the machine, and so on and so forth. An entire universe of moving parts, all perfectly synchronized, indefinitely. And for what? For a single artificial mind. A task so vast that it begins to feel almost beyond reach. And yet, life does this almost effortlessly. The problem is that we're looking at this from the top down. We've imagined a machine built all at once, wired perfectly from the outset, and expected it to sustain itself forever. But that's just not how the natural world works. Life doesn't try to assemble a complete, flawless system and then keep that running against entropy. Instead, life works from the bottom up. From single cells to complex organisms, biological systems are designed to continually replace, repair, and regenerate their components as they wear out. Proteins are synthesized and broken down. Membranes are renewed. Neurons grow new connections while pruning old ones. Every part is in constant motion, cycling energy to maintain order, even as the universe pushes towards chaos. In other words, life solves the problem of entropy not by defying it, but by embracing it. By building systems that can sustain themselves through continual renewal, rather than trying to hold a single perfect machine together indefinitely. And this is what makes biological intelligence fundamentally different from AGIRA. While our artificial system crumbles under the weight of its own complexity, life finds a way to maintain coherence, experience, and function through relentless self-maintenance, all powered by energy flows that keep entropy at bay. Life didn't try to solve the problem of general intelligence. It solved the problem of entropy minimization. Natural selection was the optimization algorithm that helped it search through a vast landscape of possibilities, and general intelligence only emerged as a consequence of that. The thing is, we're thinking about this completely wrong. We will never beat life at its own game, unless we first learn to play by the rules that life itself discovered. I think that with AGI, we really need to ask ourselves, what is it that we actually want? Because if all we want is to create a being that can briefly experience the fleeting sensation of their hand being tickled, then that's alright. We could just build AGIRA, fire her up, and let her experience the sensation before it quickly faded into static noise. But if instead we wanted to create a being that could live, that could actually experience the world, then we're going about this completely the wrong way. The thing is, we just can't ignore entropy. When we came up with the idea of a giant supercomputer that would monitor the system and figure out whether any of the parts needed replacing, essentially what we were doing was trying to counteract the destructive forces of entropy. Now, the way that we did that was by performing a computation. If part is broken, then replace. Otherwise, let it be. Again, when the system was looking at whether to strengthen or weaken a given connection, that too was a computation. If current is strong, then strengthen, else weaken. But you see, all of these computations add up. Since Maxwell, we know that one can push against the forces of chaos and reinstate order by performing computations. For example, one might choose to sort a bowl of randomly mixed M&Ms by doing the following. If M&M is green, then place in bowl number 1, etc. However, since Landauer and Bennett, we also know that with each computation comes a thermodynamic cost. Physics tells us that erasing just a single bit of information, a yes or no, a true or false, has a minimum energy requirement. This is known as Landauer's limit. Modern computers, even the most advanced supercomputers, operate at efficiency levels that are 1 billion times worse than this fundamental limit. They waste enormous amounts of energy for every simple calculation. The cell, on the other hand, operates astonishingly close to this limit. A cell's internal computations, from copying DNA to regulating protein networks, are often only a few dozen times above the Landauer minimum. Life didn't invent efficiency. Life is efficiency. If you want to understand why life exists at all, you don't start with biology. You start with thermodynamics. Because at its core, life is not a thing. It's a process, a very particular way that matter moves energy around in order to slow down entropy's advance, just long enough to create patterns that can persist. In a way, life is what happens when information learns to persist. And once you zoom in, you start to see that biology is, in a very literal sense, computation. A cell is a chemical computer running millions of parallel operations. Proteins fold into logic gates that route signals through intricate pathways. DNA stores and retrieves instructions with densities no hard drive can ever touch. Metabolism shuttles energy like a power grid, driving every operation. And enzymes read, write, and execute molecular code with astonishing precision. What looks like life is, on the inside, an endlessly running information processing engine. An ongoing computation, forever keeping entropy at bay. Every biochemical reaction in a cell is simultaneously a computation and a maintenance operation, balancing on the knife edge between order and disorder. Life sits precisely in that narrow band where computation is cheap, reliable, and sustainable. Entropy is not the enemy of life, it is the fuel. And once you appreciate that, you start to see why AGI isn't just a hard engineering problem. It's a thermodynamic impossibility. Silicon melts, circuits degrade, data centers drown in heat. But the cell keeps going, self-repairing, self-regulating, self-replicating. A machine that has learnt, across billions of years, how to turn entropy itself into the fuel of persistence. The thing is, we're trying to build general intelligence, and then solve the problem of entropy minimization. Whereas life did it the other way around. Life didn't just solve intelligence, It solved the deeper problem beneath intelligence: how to compute in a universe that punishes every bit. Evolution is less about survival of the fastest or strongest, and more about survival of the best information processors per joule of energy. General intelligence, in this sense, is not an accidental byproduct. It is the inevitable outcome of energy-constrained information systems learning to persist. From this perspective, general intelligence emerges as a natural consequence of life's thermodynamic imperatives. We can try to build general intelligence and then hope to maintain it against the forces of entropy, but this will come at an absurd computational cost. We can try monitoring every synapse. We can try monitoring the machine that does the monitoring, but there comes a point where we have to realize, maybe we just can't outdo life. On a molecular level, life is already operating near the absolute physical limits. Every cell on Earth hums just above Landauer's minimum, turning energy into information with an elegance that no fabrication plant can mimic. And if we really believe we can do better, if we truly have the hubris to think that we can outdo life, then we'll first have to contend with the fact that life has already played this game, and it has optimized every move. If we did want to create a general intelligence, realistically we'd have to solve the problem of entropy minimization first, and in doing so, we probably wouldn't create anything artificial. It'd be a synthetic intelligence instead. We keep imagining the ultimate computer as some perfect machine of silicon and superconductors, but the universe has already built one, and it fits on the head of a pin. The cell is a self-contained, self-repairing, self-replicating unit of computation, operating astonishingly close to the physical limits of efficiency. It doesn't fight entropy from the outside. It survives by turning energy and disorder into the fuel of its own persistence. Biology didn't stumble onto this by accident. It has been searching through a vast landscape of possibilities to find the best solution to entropy minimization, and in doing so, it has stumbled onto the ultimate architecture for sustained information processing: the cell, the universe's ultimate Computronium. If you strip life down to its very essence, you don't find magic. You find an architecture optimized over billions of years to compute at the lowest thermodynamic cost possible. Everything else, from nervous systems to intelligence, is built on top of that foundation. This is the part that should humble us, because if you wanted to compute at maximum efficiency under the laws of physics, you wouldn't build a silicon supercomputer. You would build something that looked almost exactly like a living cell. 3D, massively parallel, self-organizing, noise-tolerant, thermodynamically optimized to the edge of what the universe allows. If there is such a thing as a Computronium, the best possible physical substrate for sustained computation, it won't come from our laboratories. It's been alive this whole time.